Guys, welcome to another episode of CUDA Education. Against my better judgment, I have decided to, um, carry you guys along the path of modifying this application where we create an extra pipeline that basically has a bunch of moving particles in the corner. Okay? And I'm going to go through the torturous process of walking you through the process of doing that. So we're creating an extra pipeline that is going to have its own set of particles, um, and display those particles here in the corner with the particles moving around, right? Um, they're going to be as independent from what's going on in the main application as possible. Um, and these particles are going to live here. Now the reason why I have it moving around is because I want to include some level of computation complexity, right? So just like how these particles are moving around and are their position and velocities and all that stuff is being updated, I want my special little corner particles here to also be moving around. Now I did do an approach where I just wanted the particles here to basically just show up in an extra pipeline. I just wanted the particles to show up in an extra pipeline, and it didn't move around or anything. The problem with that though is that when you do that, you kind of it's just like a graphical overlay, right? And it sort of averts all of the complexity and the teaching points because it's basically just a graphical overlay. There's no like descriptor set memory operations really. There's no there's no compute whatsoever, which means there's no compute shaders, calculations being done, no real interaction between, yeah, I mean, even CPU, GPU. I mean, of course, you have to submit the draw call, which is from the CPU, but there is no yeah, it's just a very simple kind of thing where you just do a graphical overlay and you just use a graphics pipeline and that's it. So in order to sort of really get our hands dirty and get involved, even though I regret I regret this decision because believe me, it explodes the level of complexity. I basically have these particles here with its own pipeline, moving around, um, and that includes a graphical pipeline, that includes a compute pipeline, and then I try as best as possible to not involve these particles here. Can you even see my mouse anymore? You probably can't even see my mouse, can you? Right here, it's over here. I try my best as possible not to I try as best as possible not to interfere with these particles here, because if I interfere with these particles here, then I got to deal with synchronization and stuff. So it's a tall order, and I spent a lot of time working on it and also trying to just trying to make the code reasonable and digestible, if you will, for the people, for everyone. So I I already invested the time to do it. So I'm gonna break it up in chunks, and I actually haven't finished all my notes with it. So for this particular video, this will be like part one of the video. What I'm gonna do is I'm gonna carry you through my notes and carry you sort of as far as I've gone in terms of like what actually changed from the original to the the new version, and we take it from there. So let's just dive right in, guys. For this video, I'm just gonna mainly focus on the notes, right? At least the notes that I have so far. I don't really want to dive into code or anything like that. I just want to keep it conversational. See, I haven't finished it yet. There's still a bunch of stuff that needs to be done. So what we're gonna do is yeah, we'll just walk through this and I'll discuss a couple things. It's gonna be kind of a you know it's yeah, it's just high level stuff. So again, we want to create we want to create a we want to create a set of particles over here that's has its own compute and graphics pipeline, generally independent from all that's going on here, and the particles are moving around, right? So we have our own pipeline, compute and graphics pipeline with particles in it that's moving around, right? That's the whole purpose of what we're trying to achieve, right? Now there are a lot of things that we have to do, Vulkan being Vulkan, um, in order to make that happen. And I don't want to sugarcoat it. It's not. It took way more code than I expected, and it was a lot more involved. But I kind of understand why it has to be that way because, again, Vulkan gives you low level control, and as a result, you have to do more typing, more instructions in order to get stuff done, but you could optimize for performance and all that stuff, right? So anyway, let's just start. So we create corner graphics pipeline layout variable. This pipeline layout stuff actually becomes, I'm more starting to fully appreciate this whole pipeline layout discussion. And then we create a corner graphics pipeline variable. Okay. So we have our pipeline variable and we have our pipeline layout variable. Okay. And this is the create corner graphics pipeline variable and layout variable and the pipeline variable. Okay. So the thing is, now we have to create a buffer, create buffer object for corner particles. So remember, in the corner of the application, we're going to have a bunch of particles. Well, we need some memory partitioning, some memory space to sort of hold the hold the particles and specifically the compute related to the particles, right? So a lot of this stuff right here, this indentation right here, notice that it is um, it is related to more compute stuff, right? So again, the graphic stuff is simple, right? Remember I said that when I made stationary particles in the corner, that it was just like a graphical overlay, right? Because it was just basically just saying, okay, these are the particles, plop it onto the graphics thing, draw the particles, and that's it, right? So you'll notice that the graphics related stuff is rather simple, but then the compute stuff gets complicated because um, you know we have to calculate the positions of the particle, calculate the velocities of the particle, update these particles as the time goes by, as the application runs, right? So a lot of the complexity in all of this is dealing with the compute side of the equation. Okay. So use a struct, a continuous block of memory that groups multiple variables together under one name. A strut is actually a big deal in C++. Yeah, so this is another thing that I learned. Sort of as the housing, as the container, as the canopy for the compute stuff, we have this corner particles um, variable that we use to house all things related to, I guess it's corner compute particles, all the things related to, this side of the equation, right? So, um, strut a strut, even though a strut looks simple and it's something that everyone likes to gloss over and takes for granted, a strut is actually very, very important in C++. There's a lot of nuanced things and implicit things in a strut that is very important. For example, You see, like how we would have a strut with many different parameters inside of it. Um, in memory, all those parameters and all those items are sort of grouped together in memory, so it makes it easier for you to recall everything as a group. So instead of every parameter or every item being its just own independent thing, because it's part of a struct, there are certain optimizations that happen when you put it as part of a strut. But anyway, I won't go further on that. So we have compute stuff. So compute shader can read, write, update positions and velocities calculations, right? So again, I said that one of the big things about this is that we're going to have particles moving in the corner, but we have to update the positions and the velocities of these particles, right? And the compute shader has to be able to read and write the new positions and the velocities for these particles in whatever buffer that we're using, right? So the compute shader has to access this stuff. It has to be able to read it, and it also has to be able to write new information, right? Um, from I say the word shader, you guys know by now. When I say shader, that implicitly means um, GPU side stuff. So compute shader, we're doing computations on the GPU side stuff, right? And we use the language GLSL as the language to write the shader, and then that shader basically gets compiled down to spare V, right? So um, if you've been hanging with us for a while, you know that we have every time we change a shader or stuff, we have to compile the shader into spare V format so that the application can read the spare V file and do what we ask the shader to do, right? So we have the compute shader needs to read right to it. Now the graphics shader, the graphics portion, vertex buffer updates, draw call presentation to screen. Okay, so our buffer, um, the compute side has to be able to read right to it so it could update positions and velocities. The graphics portion of this buffer, or the graphics interpretation of this buffer, has to be able to see the vertex buffer updates and draw call presentation to screen. So basically, when these positions and velocities and everything is updated, graphics needs to be able to fetch the vertex buffer out of it and do a draw call and present to the screen, right? So what is the new position, what is the velocity of this particle, etc., etc. Give me the vertex updates so I could draw and present to the screen. Okay, so this is basically a read. Okay, the graphic side of it is a read on this buffer. So compute has to read and write, because obviously it has to write for obvious reasons, because it's updating the positions and the velocities. But graphics really has to read. Now, from I said this, you guys know by now that we're gonna have to deal with some level of synchronization, right? We're gonna have pipeline barrier and all that stuff, synchronization and semaphores and things of that, because we can't, we don't want to be trying to get the vertex buffer update while compute is updating the positions and the velocities, right? So you can't be updating and fetching the vertex buffer up at the same time. So there has to be some level of synchronization that has to be done with this, which we shall get into at some point, right? Note that the compute side is a lot more complicated and involved than the graphics side, as I've said before. Okay, now we have to set up variables for the corner compute pipeline, corner compute descriptor sets needed so compute shader can access memory to read write to, right? So we have to set up variables for the compute pipeline, compute descriptor sets, compute corner compute command buffer, right? Um, because of course we are doing updates and stuff, and we have commands that we need to get done, and then of course we have compute fences and compute semaphores, right? um, Remember, fences is um, CPU to GPU synchronization, and semaphores is GPU to GPU synchronization, right? So this sort of has to do with this situation here, especially I would assume the semaphores and like the pipeline barriers and stuff. Um, but then also the fences, right? So CPU to GPU synchronization, right? A lot of our code that we work on in the .cpp file, that CPU side stuff. So we know we're gonna have our synchronization stuff, um, tasks that we have to deal with. You know. Now, just as a side note, notice that when I said when I had the particles in the corner where the particles were just stationary, first of all, we didn't have any compute stuff, which means that we save on all the synchronization stuff, right? Because it's just graphics, it's just one thing, and we it was just a lot simpler. Another thing, while we're on the topic of synchronization, understand that even though we have our independent particles over here and we have the particles moving around and we try to make it as independent as possible from the main application, the main thing that's running in the main application, note that all of these tasks are being done by the same piece of hardware, right? So it's one GPU I have on my machine. It's not like I have multiple GPUs where I could say, all right, for the main application, do all this stuff on GPU one, and then for my little corner particles thing, do um, do my stuff on GPU two. No, it's the same one piece of hardware that we are running all this stuff. So even though I try to make it as independent as possible, just note that we have to we're sharing the same piece of hardware. So there has to be a level of implicit or otherwise synchronization between you know what's going on in the main application and what I'm trying to do here in the corner, right? But I'll just leave it at that for now. So we have to prepare a corner particles buffer function. This is CPU side, okay? Create a vector to point to all of our particles, okay? That's pretty straightforward. Where are you going to place our particles on the screen? So we need some position instructions. So we're saying, okay, we want our particles up here. Loop through the vector and calculate positions and speed, right? So we're looping through the vector and we are calculating position and speed. Um, Move data over from CPU to GPU. This we'll have to investigate further a little bit later, right? In another video, right? But move data over from CPU to GPU. What's the size of the data we are moving over, right? So we're trying to move data over from CPU to GPU because we're creating a vector to point to all of our particles. We're giving instructions on the position of the particles. Loop through the vector and calculate positions slash speed. Um, and then move data over from CPU to GPU. So what's the size of the data we're moving over? That's pretty straightforward. Create two buffers, one on CPU side and one on GPU side, right? So, similar to my previous videos, we're basically having a staging buffer situation where we're moving data over from the CPU to the GPU. Create a command buffer to tell GPU to transfer data into GPU local memory. See notes in code. We'll get into that in a second, but create a command buffer to tell GPU to transfer data into GPU local memory. Right. So the only language GPU understands is command buffer language, right? That's the only thing it understands. That's number one. Number two, um, the CPU can't tell the GPU the CPU can't like push stuff onto the GPU. The GPU is its own person, it has its own autonomy, and what has to happen is that you have to write a command buffer to tell the GPU to transfer data from the CPU into its GPU local memory, right? And the notes will get into that as when the time is right, right? So outline regions of data you'd like to copy, right? So what is a region of data on the CPU side that you would like to copy into the GPU side? So there's regions of data on CPU side and regions of data on GPU side, and basically you start from zero to the end of data on CPU side, and you start from zero to end of data on GPU side, right? Um, Run a flush command buffer to make sure transfer is complete before we destroy the CPU side buffer, staging buffer. Okay, so right, so we run after we initiate the copy, we run a flash command buffer to make sure, right, so we just run a flush command, not flash, a flush command to make sure that the data has successfully been transferred over, and then we destroy the staging buffer because it's good housekeeping, guys, right? We don't want to be draining system resources unnecessarily. If we don't need it and it's not relevant anymore, let's just flush it out, right? Let's let's destroy that staging buffer. Okay. So let us move on. So now we get to prepare corner compute. Okay, prepare corner compute. So interface contract for compute shader. Okay, so any descriptor set bound that says zero must contain binding zero of type storage buffer visible to compute shaders. This is related to basically um, what we had up here as our buffer, right? Corner, compute, descriptor set, all of that stuff, right? We're basically saying, okay, interface contract for compute shader, right? So we're basically saying, okay, the compute shader is expecting some information of type storage buffer and visit right, and that's visible to the compute shader. So this is sort of the creating the buffer, the storage buffer, and then just making sure that the shader can actually access that container, that memory, all of that stuff, right? Now, an interesting part that I didn't have an appreciation for, honestly, is this idea of managing the clock. Okay, so what happens is that in these applications, actually, um, in these applications, the clock, the timer is actually being run on the CPU, right? The GPU has no inherent understanding of a system clock. A CPU does, though, right? So to sort of manage the application and manage frame rates and all that stuff, um, you actually need the CPU to do that stuff, right? I was a little surprised by this conversation. I didn't see it coming at all, but you actually need a clock in order to you need the CPU clock in order to make sure that things are synced up and frames are synced up and all that stuff. You know, I don't know much more about it than that, but we have to manage the clock, and in order to manage the clock time comes from CPU, not GPU. We use push constants, so clock/time can be communicated from CPU to GPU. This is a whole conversation in and of itself. Um, we actually have a situation where the default application, the application that we just saw, without our little corner thing, of course, the application that we just saw actually it doesn't use push constants. It uses uniform buffer objects because I think it's bigger and like there are more things sharing the information, and it's just more involved, right? But for our purposes, a push constant, which is a very small piece of data, is actually perfect for our needs, and it's fewer things that are requesting the data for the push constants, on the particle side. So um, it's actually ideal for what we want. But for the main application, it's UBOs instead of push constants. I'll try and get into this at some other point, but it's actually a big deal. And actually, push constants are like they're in registers and stuff. They're in like hyper local memory and stuff, so it's super fast. But anyway, so we use push constants so the clock time can be communicated from CPU to GPU. All right, and then we create a pipeline layout, aka interface definition, right? So any pipeline that uses this layout, expect one descriptor set, set zero. The set will use the corner particles dot set layout, right? Which is just a layout that we have defined. Did we define it up here? No, we didn't define it up there. Yeah. Yeah, we'll leave that alone. Expect push constants of size float. So this part is basically this guy up here. So it's gonna have push constants and it's gonna be visible to the compute shader, right? So we know that obviously the compute shader has to update stuff, so it has to be visible to compute shader. Create one descriptor set per in-flight frame. So for every frame that we see in our corner particles, for every frame that we see, each descriptor set is an argument packet for the compute shader. VK allocate descriptor sets. Descriptor set exists but it is empty. For example, you have an envelope but the envelope is empty. So here we're just doing the legwork for we're doing the legwork for actually setting things up. Okay, um, so we have our descriptor set, which is the argument packet, and we allocate a descriptor set, and then describer write into that descriptor set, and copy buffer into the descriptor set. So this is all descriptor set stuff. I can't really dive into it now until we get into code, but you know eventually we will in another episode. Create compute pipeline. Attach compute shader sphere v file to compute stage of pipeline. So that's just our compute shaders. As I said before, our shaders is GLSL form language that it's written in for human readable, but then we actually have to compile that file down to spare v format, to a spare v format file, so that the compute the pipeline can attach to it, and the pipeline knows that this spare v file is supposed to be attached to the compute stage of the pipeline. Okay, pre-allocating the command buffers that will record and run the corner particle compute work. So we create a pipeline and then basically we get to command buffers. Give me one compute command buffer per frame. So every frame has its own command buffer. It has its own set of instructions for that particular frame. Okay. Create fences for CPU, GPU synchronization. Create semaphores for GPU synchronization. Right. And as you can see, guys, I haven't, I haven't finished going through all of this stuff. But what I want to do is I want to just go through. So we have all this stuff. I want to just go through the actual changes. So this is the original file, right? And then this is sort of the modified file that has basically all our changes for the corner particles. So we create our variables, corner graphics pipeline layout and corner graphics pipeline, as we said in our notes. Dedicated buffer for corner particles. So we have our corner particles strut. Remember we talked about the strut. And notice that this strut basically encapsulates all of this right here. So all of this right here is part of the strut, right? So there are certain efficiencies that come with it. And we know that this is part of corner particles, right? Shared buffer, shader storage buffer object for compute, vertex buffer for graphics. So it's the same buffer, it's the same buffer object, but compute uses it to read, write, and then graphics uses it for the vertex buffer information. Shader storage buffer object means a chunk of GPU memory that the shaders can read write to, but it is not private to shaders. It is shared GPU buffer, backed by the device memory, VRAM, or device local memory. It is the same memory but interpreted differently by compute or graphics pipeline. The compute pipeline uses it to update positions and velocities via its shaders, and the graphics pipeline uses it to draw the particles, right? So just along the lines of what I was talking about, right? So we have our compute pipeline stuff, what it bound as a storage buffer accessed in a compute shader, read write, and then we have the position and velocity information, right? So that's the compute stuff. Graphic stuff bound as a vertex buffer, right? So here it's bound as a storage buffer, but for graphics it's bound as a vertex buffer, accessed in a vertex shader, and read only, positions for drawing, right? So as we said, graphics only reads. And then we actually create, this is not commented out, we actually create the buffer variable, right? So this is not commented out. I know it's hard to see here, guys, but this is actually um, not commented out. So now we get to compute pipeline for corner particles. Compute is doing this. Given the previous frame state, compute the next frame's state and store it. Okay? So that single sentence explodes into complexity. Your corner compute pipeline must handle responsibilities, right? So this is where I was talking about the complexity of the compute pipeline, right? Instead of just plopping particles on a screen in the corner, we're actually trying to like update the particles because the particles are moving around in the corner, right? Your corner compute pipeline must handle responsibilities, why it exists. Persistent buffers, right? Positions, velocities must survive across frames, right? Very important. Descriptor set, shaders must read write buffers explicitly. Pipeline layout defines memory and push constants. Push constants, CPU time must enter the GPU, right? So again, we're talking about that clock thing, right? We have to have that clock. Command buffers, dispatch must be recorded explicitly. Synchronization, GPU must finish writing before graphics reads, right? So I was talking about here that the CPU shaders need to finish updating the stuff in memory, the calculations in memory, before the GPU, the graphics reads it, right? Fences, CPU must not overwrite buffers still in use. So, right, so that's just CPU side stuff. Semaphores, right? Compute graphics ordering, okay? Barriers, enforce memory visibility, right? So the barriers is more just making sure that there's no violations in regards to accessing memory and all of that stuff, right? um, this is more of a buffer memory stuff. Queue ownership, compute and graphics may be on different queues. All of that exists because the data is being mutated, right? So as you can see, the compute side has a lot of stuff going on, right? So we set up our compute variables, right? Still part of our strut, We have a set layout variable, descriptor set layout variable. We have a pipeline layout variable. We have a pipeline, and uh, we have this descriptor sets, we have command buffers, and we have fences and semaphores, right? So a lot of stuff going on here, guys. A lot of stuff going on. So then we continue down, and then we good housekeeping, guys. We have to destroy all the things we are created. This is part of the destructor, right? So good housekeeping. Um, prepare corner particles buffer. So here, as we said in our notes, we have a vector of particles, right? And then we do some math just to make sure um, we make sure the calculations for the particles are done. So I guess yeah, the calculations for the particles is done here now. Yeah, the calculations for the particles are done here. So we loop through each one of the particles and we update. We update based on what we need. If we change this variable here is where we get the speed of the particles, right? Um, let's move the data over from CPU to GPU. First, figure out the size of the data that we have to move. So again, we calculate the size of the data. So we have init size, right? Because init was our vector times size of a vec4 a vec4 data type. We create two buffers, one on the CPU side and two on the GPU side. One on the CPU side and one on the GPU side. So we have our buffer and we create our buffers, right? And then we move. This is a CPU to GPU transfer. So a simple mem copy will not work because the CPU does not have that power. Only the GPU can transfer into the local memory, but GPUs only speak in command buffer language. So we have to create a command buffer that tells the GPU to transfer this data into the local memory. That is what this is all about. So here we create a mini command buffer. We create a mini command buffer to actually do the transfer from CPU to GPU, right? Again, GPUs only speak in command buffer language, right? So start copying from byte 0 of the staging buffer and write into byte 0 of the device local memory. Size represents the total bytes to be transferred, right? So 0, 0 size, right? Command to copy data between the regions, right? So we actually copy the data into the regions. This and then we do a flush. This ensures that the transfer is complete before we destroy the staging buffer, right? So we do a flush here to make sure it's complete before we destroy. And then we destroy the staging buffer. All right. All right, we're at 37 minutes right now. So let's just plow through this. So prepare corner compute. So now we have to prepare corner compute. This declares the interface contract for the compute shader. There'll be a descriptor set. It contains binding 0. Binding 0 is a storage buffer, and it's visible to the compute stage, right? So we do all of that, right? So we do the descriptor set stuff, the bindings, all of that stuff. What actually changes every frame? Even in CPU only simulation, some things cannot be known purely on the GPU. So we have, um, this delta time thing. Delta time comes from CPU timers, OS windowing system, VSync, and frame pacing. The GPU has no global clock tied to your frame look, so DT must be supplied each frame. So push constants, we have all of that as we use push constants to communicate the we need push constants so that the clock time on the CPU can be communicated to the GPU and used in the shaders, right? So we do that right here. So create pipeline layout, aka interface uh, definition. This tells Vulkan any pipeline that uses this layout expect one descriptor set 0, that uses the corner particles dot set layout, expects push constants of size of float, and visible to compute shaders, right? So we do all of that stuff here, right? And we actually create the pipeline layout here. And then for the descriptor sets, we loop through all of the frames and we allocate a descriptor set to each frame and then actually write the descriptor set. So that is, all of the information that we have encapsulated in, for our descriptor set. And this is where the descriptor set actually gets updated and written. Um, and then we actually get to the business of creating the pipeline. So where is right? So we create compute pipeline here, right? And we'll get into all of this in another video, right? But we create the compute pipeline here, and we associate a command buffer for each corner particles. We associate a command buffer for each of the frames, and then we also have to deal with fences and semaphores. And then I think I just stop right here because it is a lot. Creative fences and semaphores, right? So the updated application is going to have all of that, all of that information. Again, just as a refresh, this is our default application, right? And we're trying to get corner particles here that moves around, and we have to, you know, do all of that. Um, Really and truly, after, so I'm literally stopped right here, but there's a couple more things that we have to do in order to make this happen. This is basically after we do, you know, after this, I mean, it's a couple more things that are considered changes. So all of this stuff in yellow that we're gonna have to do in order to get our application running. Yes, guys, it's a lot of code to do a small amount of stuff, but um, it's a pain that we have to go through. So anyway, guys, that's it for this video. I hope I haven't discouraged you guys. It's a lot of legwork initially, but once you get, once we have our pipeline set up and we have our particles in the corner, you've done most of the legwork, and then you could start to do other things that you want, and it wouldn't be as painful because you sort of have the boilerplate stuff done already. Anyway, guys, that is it for this video. If you want to be able to run this stuff on your machine, tutorial number 1 installs the Vulkan SDK. Tutorial number 13 installs the Vulkan examples, including this one. I assume a Windows-based machine with a Vulkan-capable GPU. And if you want to run the ray tracing stuff, you also have to make sure that your GPU can run ray tracing. Um, this example is not ray tracing capable though. All right. But thank you guys for watching. I will be back with another video.